faithfully delivering value, interpreting great books worldwide. Hi, I'm Sally from Book Talk. Today we're exploring The Sun in a Bottle, subtitled The Strange History of Nuclear Fusion. Over recent decades, coal and oil resources have been dwindling fast. Humanity's thirst for energy is growing ever stronger. When scientists discovered the sun's nearly endless energy, they hatched a bold plan: build a tiny man-made sun on Earth to solve our energy woes for good. Oh, this book chronicles humanity's quest to create a sun? It sounds like just another grand human conquest of nature through science. But this time, humans failed. The book's subtitle is The Strange History of Nuclear Fusion. So what makes it strange? The weird part is that scientists abandoned the core values of truth-seeking, honesty, and critical thinking. Once they saw that building a sun could bring riches, fame, and even military or political power, they all lost their way and stopped respecting science. They skipped scientific checks, broke academic ethics, faked results, and kept claiming we'd tamed the sun, only to crash and burn every time. The author Charles Seif has a math master's from Yale University and teaches journalism at NYU. He witnessed this whole scientific circus firsthand, and using solid historical data reconstructs the bitter saga of artificial suns, exposing the arrogance, greed, and hypocrisy in science. All right, I'm going to break it down into military and energy angles so you can glimpse humanity's sun dream that spanned over half a century. First up, let's chat about how a man-made sun packs a punch in warfare. When folks first realized the sun's power, they didn't think energy, they thought weapon. So how do we harness this force? Well, first off, we gotta grasp the basic way the sun releases energy. In fusion, nuclear means the atom's core can be split or fused. Smash two small nuclei together to form a bigger one. That's nuclear fusion. Flip it around, crack a big nucleus into smaller bits. That's nuclear fission. Both fusion and fission are types of nuclear reactions. Absolutely, that's the fundamental principle behind nuclear weapons. Human understanding of nuclear reactions began with fission in 1898 when Madame Curie discovered radium, a miraculous substance that gave scientists their first glimpse of nuclear power. Radium seemed to create energy from nothing. Without chemical reactions, it heated itself like a tiny furnace while producing radioactive materials. Even today, notebooks Madame Curie used over a century ago must be stored in lead-lined boxes. The radium dust contaminating them still radiates energy continuously. Thermodynamics says energy can't appear from nothing. So where does radium's heat come from? The answer lies in Einstein's famous equation, E equals mc squared. Energy equals mass times the speed of light squared. Mass and energy are convertible, and converting just a tiny bit of mass produces staggering energy. For instance, when a kilogram of radium undergoes fission, it becomes slightly lighter radon, losing only 23 milligrams of mass, about a pill's weight. But through mass energy conversion, that little pill's worth releases energy equal to 400 tons of TNT. Humanity was instantly mesmerized and deeply shaken by fission's unbelievable power. Thus, the atomic bomb was born. Its fuel was uranium-235, highly unstable. Hit it with a subatomic particle, and it splits into smaller nuclei, releasing neutrons. These neutrons act like dominoes. One neutron from fission can trigger over 1 trillion atomic splits after about 40 collisions. It's the terrifying chain reaction in atomic bombs. Nuclear fission gave humanity a devilishly terrifying weapon. America's Manhattan Project built the first atomic bomb. Its leader, Oppenheimer, later plunged into deep remorse. For a scientist with a conscience, the atomic bomb meant science's fall from civilization's altar. He even blurted out at the UN, disregarding the president's dignity, "Mr. President, my hands are stained with blood." Radium's Pandora's box was opened. The atomic bomb was just the beginning. A force thousands of times stronger was coming. This unprecedented power is nuclear fusion, the energy source that's kept the sun burning for billions of years. Nuclear fusion is the reverse process of nuclear fission, but their operating conditions are vastly different. As I said earlier, when radium undergoes fission, it's like a self-heating furnace. No action needed, it just happens at room temperature. But nuclear fusion is different. It demands extremely high conditions to work. We know atomic nuclei are positively charged, so two positive nuclei repel each other. To force them together, you need massive external force, high pressure, and high temperature. The high pressure brings nuclei close enough. High temperature makes nuclei collide fiercely. Take the sun as an example. It's packed with hydrogen atoms. Under high pressure and temperature, two hydrogen nuclei smash together, forming heavier helium atoms and releasing energy that heats the sun. Originally, this process would make the sun burn hotter and hotter until it explodes. But in reality, heat causes the sun to expand. When it expands, pressure drops, so atomic collisions become less frequent. The fusion rate slows automatically. Fusion decreases, temperature falls. Then, as temperature drops, the sun contracts, pressure rises again, increasing fusion frequency. Thus, the sun maintains this balance, steadily releasing energy. People found that fusion produces far more energy than fission. That's because, for the same mass of nuclei, fusion causes more mass loss, converting to way more energy. Its power is tens to thousands of times greater than fission. When humanity uncovered the sun's secret, atomic bombs seemed trivial. Some wanted to harness the sun's power to create fusion bombs, hydrogen bombs. This person was one of the darkest scientists in American science. Edward Teller was part of the Manhattan Project, but he had no interest in atomic bombs. He wanted to go big. He aimed to build hydrogen bombs. I found a peer of Teller once said, "I truly believe the world would be better off without Teller." On November 1st, 1952, a hydrogen bomb named Sausage made Alugalab Island in the Pacific vanish instantly. This was equivalent to the explosive power of 700 atomic bombs dropped on Hiroshima, humanity's first time unleashing the sun's might on Earth. Teller, the mastermind behind this catastrophe, observed Earth's tremor through a seismograph on the opposite side of the planet and knew he'd succeeded. Yet, America's triumph lasted just 3 years before the Soviets detonated their hydrogen bomb, similarly unleashing the sun's fury upon Earth's inhabitants. In the frenzied US-Soviet arms race, destroying Earth was becoming frighteningly easy. Pacifist protests surged back and forth. People in both nations found this power too terrifying and began curbing fusion weapon development, but Teller, intoxicated by it, refused to stop. To continue his fusion dream, he claimed hydrogen bombs could benefit humanity, not just wage war. This coincided with Egypt nationalizing the Suez Canal, seizing this vital waterway from Western powers. Madman Teller immediately proposed, simple, detonate hydrogen bombs along Israel to blast a new canal through pro-Western territory. He even considered bombing the moon with H-bombs to reduce its climatic influence on Earth. Thankfully, none of these insane ideas materialized. Peaceful H-bomb use proved nearly impossible. If scientists wanted to harness solar power without self-destruction, they needed to contain this force. Like bottling the sun, take only what you need, making fusion controllable and measurable. So the biggest question became, where do we find a bottle that can hold the sun? Next, let's explore the second aspect, using fusion for energy production. It centers on bottling the sun. At first glance, building a container sturdy enough for a burning star seems impossible. Since fusion generates humanity's greatest known energy, what material could withstand it? Fusion temperatures reach tens to hundreds of millions Celsius. Even diamond would vaporize instantly. Yet scientists actually found such a bottle, not made of matter, but magnetic fields. Let's see how magnetic fields act as bottles. Electromagnetic laws show that moving electric charges are affected by magnetic fields. We know atoms are electrically neutral and unaffected by magnetic fields, that the electrons and nucleus that make up an atom are charged, one negative, one positive. In fusion reactions, under extreme heat, atoms separate into freely moving electrons and nuclei. At this point, both types of charged particles become influenced by magnetic fields. If a magnetic force is applied perpendicular to their motion, particles change paths, moving in circles instead of straight lines. The stronger the magnetic field, the smaller the circular path, so we can trap these blazing particles, making them spin in place without escaping. A perfect bottle with the right magnetic field. Based on this principle, scientists finally designed the bottle. America pioneered it, naming the device the Columbus machine. In 1955, American scientists saw signs of fusion in the Columbus machine, the production of neutrons. Why were neutrons produced? Because fusion fuel is deuterium and tritium, both isotopes of hydrogen. Isotopes have the same number of protons, but different neutrons. Deuterium has one neutron, tritium has two. When they fuse into helium, which has two neutrons, the extra neutron becomes a byproduct. Since neutrons lack charge and aren't confined by magnetic fields, they fly out. Thus, detecting neutrons is the best sign of fusion. In the American experiment, tens of thousands of neutrons erupted, sparking jubilation and an immediate announcement of fusion success. But was it really that easy? Soon doubts emerged. In true fusion, neutrons should pour out equally from all directions with uniform energy. But in the American experiment, neutrons from different directions had uneven energy. After investigation, the results were disheartening. Those neutrons did come from fusion, but not high-temperature fusion. Due to instrument instability, some extremely hot nuclei interacted with colder ones fusing to produce neutrons. You might ask, isn't this all nuclear fusion? What's the difference? The fusion we want is for energy, getting two blazing atomic nuclei to combine spontaneously. But in this experiment, two hot nuclei didn't collide. Instead, a hot and cold nucleus met. They'd never react spontaneously. It's like adding cold water to hot. The more you add, the cooler it gets. To keep it hot, you need to reheat it. So this fusion uses more energy than it produces, totally pointless. America's attempt failed, but they weren't the only sun dreamers. Across the ocean, Britain built a bottle called Zeta. In 1957, the British also detected neutrons. Though some doubted, self-congratulatory cheers drowned out skepticism. Most researchers firmly believed they created the world's first artificial sun. The US and UK were sharing fusion research, so Britain's apparent success deeply embarrassed America. To score political points, US media spun it as a joint achievement. They even claimed both nations were neck and neck. Global newspapers erupted. Countries like Sweden and Japan built identical Zeta devices, all claiming fusion success. Nuclear prospects seemed to bloom everywhere. But cooler heads prevailed. Scientists sensed something was off. Using the same method that debunked the Columbus machine, they found Zeta's neutrons also came from hot-cold collisions, energy-draining fusion. Britain was stunned. It was all fake. The US and other successful nations were utterly humiliated. They'd ignored past warnings and made the same mistake twice. And blinded by optimism, glory-seeking arrogance, and greed, these scientists faced global disgrace. Fusion's allure was so potent that scientists skipped verification just to claim they'd achieved it first. After the Zeta incident, concluding, scientists worldwide finally grasped how daunting it truly is to harness the sun's power. After the UK and US failures, a third contender emerged, the Soviet Union, inventing a revolutionary bottle called tokamak. Its groundbreaking design introduced laser technology, Laser light differs from flashlight beams. Flashlights mix colors together, but laser light is one pure color, traveling far without spreading or fading much. If photons in regular light are a chaotic mob, laser photons march like a disciplined army. With lasers, we can target a tiny spot with extreme precision, pouring massive energy into it. Inside tokamak, lasers blast fuel from all sides, rapidly heating and compressing it to trigger fusion. Overnight, physicists worldwide ditched Columbus and Zeta machines like scrap metal, rushing to build tokamak. Timed with the first oil crisis, tokamaks reignited dreams of limitless energy, costing millions to billions. But larger tokamaks still failed. Uneven laser heating made lighter electrons explode before heavier nuclei could fuse. With US, UK, and USSR experiments failing, fusion remained a distant dream. Both magnetic fields and lasers faced technical nightmares. Solutions drove costs sky high while results disappointed. Then came the question, was there a cheaper way? Thus emerged cold fusion, 20th century science's biggest flop. Enter our leads. Chemists Fleischmann and Pons from Utah University. They noticed palladium metal could absorb huge amounts of hydrogen atoms. So they theorized, replace hydrogen with deuterium, fusion fuel. More deuterium absorbed means tighter crowding in palladium. Wouldn't that trigger fusion when they get infinitely close and collide? For decades, fusion's accepted conditions have been high temperature and extreme pressure. Previous failures happened because these conditions are hard to control and prohibitively expensive. Achieving cold fusion at room temperature would undoubtedly crack the toughest nut. So these two started experimenting in their kitchen and actually found palladium absorbed deuterium while generating heat. They immediately declared they'd triggered fusion. Now, both swiftly submitted reports to the U.S. Department of Energy seeking funding. Coincidentally, Jones, an Energy Department paper reviewer, was also researching room temperature fusion. When the three met, Fleischmann and Pons grew uneasy. Oh no, what if Jones publishes first? Only the first to master cold fusion would become a global hero, claiming all money, glory, and power. Second place meant nothing, so they agreed. For fairness, each team would write separate papers. On the same day, they'd meet at the airport, hand papers to FedEx, and send them to Nature, the top journal, for judgment. And then Fleischmann and Pons jumped the gun. A day before the deadline, they held a grand press conference at Utah University, announcing room temperature fusion to the world. This wasn't just betrayal, it violated scientific norms. Proper protocol requires rigorous verification after initial results, before peer-reviewed publication. Announcing via press conference, without data or papers, was astonishingly irregular. Media hype brought flowers, applause, and cash. Fleischmann and Pons basked in glory, while physicists worldwide scrambled like ants on a hot griddle, desperate for experimental details. But the pair dodged questions. They had no real confidence in their results. If it were real fusion, there should be about 1 trillion neutrons per second, but they only detected around 20, yet they stubbornly took this as evidence of fusion. No surprise when scientists worldwide repeated the experiment. They quickly found this whole thing totally unreliable. Besides the neutron issue, the two claimed to have detected heat, which also faced skepticism. How can we prove the heat came from fusion, not somewhere else? Maybe other factors caused the metal to heat up. This calls for a control experiment. Replace the deuterium-containing water with regular water and repeat the exact same test. This kind of control experiment is a basic step even a first-year science student knows is necessary. But when asked why they didn't publish the control experiment, Fleischmann said, "I'm not prepared to answer that question." Kantz responded even more bluntly, "Control experiments aren't needed." Ultimately, cold fusion at room temperature was proven impossible. It was a humiliating farce. Yet fusion's allure has become a mesmerizing force that not even scientific facts can shatter. Soon, the historical farce played out again. This time, fusion was tangled in blatant academic fraud. An American scientist named Taylor Yarkon submitted a paper to Science magazine claiming he achieved a new fusion method called bubble fusion. Uh, this fusion is based on sound converting to light. Ever had that experience? When you do a belly flop dive, you feel your stomach sting by the water. At that moment, water acts more like a solid than a liquid. This isn't just a metaphor. Water really can show solid traits under certain conditions. It can crack like a solid. When water cracks, it creates tiny vacuum bubbles. Sound waves in the water then press on these bubbles, and the squeezing generates heat. And when heated to tens of thousands of degrees, it releases light. That's the principle of sonoluminescence. Taylor Yarkon's paper stated he could use this bubble heating to achieve fusion. It had data, control experiments, and rigorous methods, all seemingly correct. But people were still skeptical. Did the experiment really succeed? While everyone was speculating and waiting, someone published the same research article in another journal called Nuclear Engineering and Design, proving bubble fusion is feasible. Taylor Khan quickly declared this a great achievement, saying his experimental results were independently verified. He even went on BBC and bluntly said, "I hope I get the Nobel Prize." But soon people found out the bubble fusion experiment couldn't produce neutrons. It was a total failure. So where did that independently verified paper come from? Turns out Taleyarkhan wrote it himself, and the listed authors were just lab researchers who did almost nothing. It was a one-man show, a total sham. Taleyarkhan used to be a respected engineer, but in his ruthless chase for the Nobel Prize, he used academic fraud and ruined his career. Repeated failures and massive costs made folks realize that no country or person alone can master the sun's power. Why don't we pool resources and build an international nuclear reactor? Couldn't that lead to a breakthrough? That human nature is greedy. Even though everyone thinks a big international reactor is awesome, there's only one reactor site. Everyone fought to have it in their country. So the US, Germany, and Japan each built one. The whole pool resources and cooperate idea vanished. Fragile teamwork didn't last. After burning cash with no results, the US Congress quit because they want ROI, not pure science. Save the money. At this point in the story, we see humanity paid a huge price for the dream of endless energy. But is this energy dream really that wonderful? Some say fusion provides clean, safe energy, not like fission that makes harmful radiation. But here's a secret: fusion ain't so clean. That's because fusion churns out tons of neutrons, and neutrons don't get trapped by magnetic fields. So they leak from the sun in a bottle. These neutrons zip through ordinary stuff, turning stable atoms radioactive. If they'd hit your body, they kill cells and cause cancer. It's an open secret, but folks still crave all that power. So that's the bizarre history of nuclear fusion. For over half a century, the scientific community seemed collectively cursed, forgetting painful lessons and repeatedly declaring fusion's success from flawed experiments. Time and again, it ended in farce. If scientists can't shed this vain self-deception or explore nature with humility and reverence, bottling the sun will remain humanity's unattainable pipe dream. All right, that wraps up The Sun in a Bottle. You'll find reading notes below the audio. See you tomorrow.